So as we saw in the previous example, it's possible to do an analysis of a digital logic function in which you just consider ones and zeros, but the problem is that if the inputs change at all, then that analysis is no longer valid for the particular combination of inputs. Instead, what we can do is we can do a symbolic logic analysis. And in that case, you're not going to be tracing ones and zeros through the circuit, you're going to be tracing variables like A and B and C and D. And then what you'll end up with is you'll end up with an expression that represents the logic that is contained within that circuit. And that's what we're going to do in this example. So you can see up here we start with A NANDed with B. So of course the core functionality is A and B, but we have to have a bar across the entire thing to represent the fact that that's a NAND function. Similarly down here the core functionality is C or D, but we have a bar to represent the fact that these are NORed together. Now that A NAND B is going to carry through to the input of this OR gate, and the C NOR D will carry through there. C NOR D will also go here, by the way. That one becomes pretty easy to invert because we just put two inverters and they cancel each other out. So the bar and the NOT gate cancel each other out. The output of the OR gate is a little harder though. We end up with A NAND B ORed with C NOR D. You'll notice that when we did the previous example with just ones and zeros, it was always just ones and zeros, and it was always pretty relatively easy to trace the ones and zeros through. In a symbolic analysis, as you go from left to right, more and more of the function needs to be included, and it gets to be more and more complex. So now I can write the final function f over here. I'm going to go ahead and write that on its own line because it's going to be pretty long. I'm going to say f is equal to, it's the AND of the two things that are coming in as the inputs. So it's A NAND B or C NOR D, and then that's ANDed with C or D. So I now have a logical expression, a Boolean algebra equation that represents exactly the work that this digital circuit is doing. It is completely equivalent to the circuit. If I have the equation, I don't need the circuit. If I have the circuit, I don't need the equation. And furthermore, if you tell me what the combinations of A, B, C, and D are, I can then go back and figure out what will be the output F. As a matter of fact, the previous example that you just watched is actually just a special case of this example in which A, B, C, and D take on particular values, yielding a particular value of F.